For our exothermic experiment, we utilized a thermometer, a 150 ml beaker, warm water, paper cups, hydrogen peroxide, yeast, and a stirring rod. Now, we transition to procedure B, our exothermic system. We pour 45 ml of hydrogen peroxide into a 150 ml beaker and measure and also record the initial temperature of the hydrogen peroxide, which registers a steady 32 Celsius. In a separate cup, we mix 5 grams of yeast with 10 ml of warm water. Now, we pour the yeast mixture into the beaker containing the hydrogen peroxide and stir gently for about 10 seconds. Observe the reaction as foam rises rapidly in the beaker. The yeast acts as a catalyst, helping the reaction occur more quickly. Record any visible observations such as rapid foam production and temperature changes. The thermometer climbs aggressively, allowing us to record the highest temperature reached, which peaks at 45 Celsius as the beaker feels warm and hot.
For exothermic decomposition of H2O, delta T is minus 32. H equals positive 13 degrees Celsius. Using Q minus MC, delta T will be changed. Q equals 45 times 4.2 times 13, which gives us positive 2,457 joules. Because we need a 6% solution, the actual mass of pure hydrogen peroxide is 2.7 grams. Finding the moles, and we divide 2.7 grams by the molar mass of 34, giving us 0.0794 moles. Finish our enthalpy change, delta H equals Q over N, 2457 joules divided by 0.0794 moles equals 30.94 kilojoules per mole. Since this is an exothermic reaction that we see, we write it as a negative value, negative 30.94 kilojoules per mole.
Now for the first experiment, it is about endothermic reaction. We will be using a glass thermometer, a bottle of white vinegar, a beaker, baking soda, 2 paper cups, an electronic balance, and a spoon for mixing. First, pour 45 ml of the vinegar into the beaker. Then use the thermometer and measure.
Now, weigh around 4.5 grams of baking soda using the electronic balance.
We can put it separately and just put it in. Then, record the initial temperature of the vinegar.
Afterwards, add the baking soda into the beaker with vinegar and use the spoon to mix it for about 10 seconds. There should be effervescence when the baking soda and vinegar react. Use the thermometer once more to measure the lowest temperature reached by the solution and record it. Now, let us look at our hypothesis for this experiment. First, we hypothesize that the temperature of one reaction will decrease while the temperature of the other reaction will increase. Second, we predict that the exothermic reaction will show a greater temperature change than the endothermic reaction. Let's look at our experimental results side by side. For vinegar and baking soda, the T initial was 29 degrees Celsius and the T final was 26 degrees Celsius, giving a delta T of -3 degrees Celsius. For hydrogen peroxide and yeast, the T initial was 32 degrees Celsius and the T final was 45 degrees Celsius, giving a delta T of +13 degrees Celsius.
To quantify our endothermic system, we first find the temperature change. Delta T is equal to T final minus T initial, which gives us -3 degrees Celsius. Next, we calculate the heat change using the formula Q equals mc delta T. Plugging in our mass of 45 grams and specific heat capacity of 4.2, Q is equal to -567 joules. To find the number of moles, N, we take mass over mR. 5 grams divided by 84 grams per mole equals to 0.0595 moles. Finally, for the enthalpy change, delta H equals Q over N. -567 joules divided by 0.0595 moles give us a final delta H of -9.53 kilojoules per mole. From the results, it was clear that the two reactions showed different temperature changes. The reaction between vinegar and baking soda caused the temperature to decrease, indicating that heat was absorbed from the surroundings, showing that the reaction is endothermic. Bubbling was also observed due to the production of carbon dioxide gas during the reaction.
On the other hand, the reaction between hydrogen peroxide and yeast caused the temperature to increase, indicating that the heat was released to the surroundings, making it an exothermic reaction. Foam was produced because oxygen gas was released when hydrogen peroxide decomposed. The temperature increase in the exothermic reaction was greater than the temperature decrease in the endothermic reaction, suggesting that more heat energy was released in the exothermic reaction than the amount of heat absorbed in the endothermic reaction. These observations support the principle of thermochemistry, which explain how energy is transferred during chemical reaction and can be related to everyday life in instant cold packs and hand warmers.
In conclusion, the objectives of this experiment were successfully achieved. We confirmed that the vinegar and baking soda reaction is endothermic due to its temperature decrease, while the hydrogen peroxide and yeast reaction is exothermic due to its temperature increase. The results also showed that the exothermic heat release was significantly greater than the endothermic heat absorption. Overall, this experiment clearly demonstrated the core principles of energy change within thermochemistry.